Okay, so welcome to the first day of my new series, which is Studying Until I Get an Applied AI Job. So, today I studied about fine tuning and the low rank method of fine tuning LLM models. So, I will summarize whatever I studied today in 5 to 10 minutes, and this is what I will try to do every day in this journey that I have taken. So, to start off, what is fine tuning and why we need it? So, LLM training is very expensive, it requires a lot of GPU power, and that is something that only these big companies can do. But what we can do, and what is slightly less time taking or slightly less expensive, is fine tuning these LLMs. So now the LLM is trained on data available on the internet, and that data is very like it's, it's the data is very generalized. So an LLM is good at things like learning grammar or basic mathematics. But what the LLM is not good at is very specific tasks. Like, for example, if you as a LLM to do something a CA does, which is very financial heavy work, it might not be able to do. So that is where fine tuning comes in, where the LLM is trained on a specific data set for the use case that you have for the LLM. So in the CA case, it would be financial data. And what the LLM we have seen is very good at is learning from these smaller data sets and then being very good at this specific task. So this process of learning is called fine tuning the LLM. Now, when we think about fine tuning, we do not want to fine tune the full model. Now, the models that are there in the market today, they have 40 billion, 50 billion parameters. It is not easy to, like, for a company, a smaller company, to fine tune such big models. Like, it takes a lot of memory to load the full model in the GPU. So think about how expensive it would be to train such a model, like how much virtual RAM would be needed for this. One more reason is, if you change the full model, like if you have for the CA case, let's say you have little bit data and you train the full model on that data. What this leads to is the LLM tends to forget the the general knowledge concepts that it has learned. Like, it will tend to forget basic grammar, basic math, when it is so focused on learning from that small data set. And this also leads to something called as model overfitting, where we see that the LLM tends to just memorize from the smaller data set, and it's not really learning, it's just memorizing your input and output data. Also, like, if you take a base LLM and you fine tune it for different tasks, it would be very tough to store all of these weights. If, let's say, you have 4 tasks and 40 billion parameters each, and everything you have fine tuned for that specific use case, that means 4 times 40 billion parameters you would need. Yeah, so that is why we do not fine tune the whole model. And let's now come to a method of training which follows these principles, which is called low rank training. Now, tomorrow I'll go into the detail and I'll implement this method of fine tuning. But for today, I'll just go through the brief about this model. So in lower rank training, first I explored the maths behind this, which is what is the rank of a matrix. Now, the rank is defined as the number of genuinely independent directions in a matrix. So, this could be rows or columns. But it's like more important to understand what this means in an LLM context. So, if you look at this matrix, the first row and the second row are basically the same thing. Like, if you multiply row 1 with the number 2, you would get row 2. So, if you look at this in the geometrical space, these three rows that you have pretty much gives you a 2D space, because the second row is a combination of the first row. So, if you combine these three rows, in any which way that you combine, you would only end up in 2D space. So, what I could understand, like by taking this concept into the LLM context, is that the information in the W matrix is worth two rows. So when you say a matrix is low ranked, you would say that the directions of that matrix has provides low amount of information. So that is the claim behind the LoRA method of training, which says that the change in W would be low ranked. Now, this is what we discussed before, where the task in hand is to tune the weights of your already pre-trained model in such a way so that you learn intricacies about your new data set. Now, you do not want to forget all the information that you have learned already from your training. That is why this is a good claim to have. This would satisfy all the points that we already discussed, and this would make it easier for us to tune the model. Now, here we can see that the LoRa claim is the new W that you get is your W naught, which is all the training that you've done. Let's say 1000 into 1000 parameters plus a change in W. Now, how we calculate this change in W, we'll come to later. But I hope we understand why this change in W would be a low rank matrix. Okay, so now, this just says that the new task nudges few features. So let's say like your W naught represents all of English, all of maths. On top of that, you just want to make few nudges, which would be low rank nudges. Maybe let's say in 16 directions, your vectors would change. But overall, this would give you the final W, which would be a more, which would have all the data from your training, but which would also be better at the specific problem you're trying to solve. So, in low rank, what we do is the change, we try to break it down into two vectors. One is your B vector and one is your A vector, where if you see previously, your W has 1000 into 1000 parameters, but now your B, if you choose your rank to be 16, there will just be 16,000 times 2, which is like you're learning lesser amount of parameters, which is what we wanted to do when we discussed why not fine tune the full model. So, yeah, I guess for today, this was a very interesting topic to start with, but tomorrow I wish to go deep into this fine tuning algorithm, probably write some code and also implement this algorithm. Thank you for joining.